Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 3.2, day 1, entitled Polynomial Functions and Their Graphs. And today we're going to talk about the first 3 objectives. We're going to graph basic polynomial functions. We're going to talk about their end behavior and their leading coefficients. And then we're going to use the zeros or the solutions to help us graph polynomials. Now we've already talked about polynomials of the second degree, which are all parabolas. So today we're going to talk about more complex polynomial functions. And this little box does a really good job of reminding us of some common terminology when we're dealing with a polynomial function. And this is the general form that we've seen before. But remember that the a sub n and the a sub n minus 1, etc., those are all going to be our coefficients. The constant coefficient is the a sub 0 that's added on at the end. The leading coefficient is going to be the a sub n in the front. And then your leading term is going to be the a sub n times x to the nth. And your degree is actually going to be the n on this x to the nth as well. That'll be the degree of your polynomial. And this next slide does a better job of showing that with actual numbers. Okay, so here's your polynomial. It's a degree 5 because that's your largest exponent. So we want to, again, put them all in descending order. So once they're in descending order, your degree will be whatever that first term's exponent is. Then you also have your leading coefficient on that first term once they're in descending order. And again, once they're in descending order, that's going to be your leading term. You can see all the coefficients. And then you can see your constant term. And you can see all the exponents on the other variable terms as well. Okay, so just keep that basic terminology in mind as we're going through this chapter. And we've touched on this a little bit already too, about the different degrees of polynomials you can have. If you have a polynomial with degree 0, that means you'd have x to the 0 power. And remember, that's just 1. So 1 times anything is just that thing. Okay, so if you had a number in front of the x to the 0, you would have 3 times 1, which would be 3 for that first example there. First degree is just going to have x. So on here they have 4x minus 7. Degree 2 is going to have an x squared as your leading coefficient. You could have an x added onto it. You could also have a number added or subtracted onto the end of it. And then degree 3 is going to have your leading term that has x to the third, then an x squared. It could also have an x, or it might not. And it could have your constant term at the end, or it might not. Remember, anything that has just one term is called a monomial. 2 terms is a binomial. 3 terms is a trinomial. Anything beyond that is going to be a polynomial. Okay, so we're going to talk about some basic graphing now, some features of the polynomial graphs. And some of this we've seen before, but to start off, remember that when polynomials are of degree 0 or degree 1, they're just lines. If it's degree 0, it's either going to be a horizontal or vertical line. If it's a degree 1, that's going to be basic slope-intercept form, so it's going to be a straight line. A graph that's degree 2 is going to be some type of parabola. And anything beyond that is going to get a little more complicated. But the nice thing is that the graphs are continuous and they're smooth. They have curves in them. They don't have any breaks. They don't have any sharp points to them. They don't have any corners. And the book does a good job on page 233 of illustrating some of those pictures that have the sharp points or the corners or the cusps. That's what they call those sharp points. So if you want to see some examples of what a polynomial function isn't, you can look on that page. There's a chart in your book. But our polynomial functions are going to be nice and smooth. Even the linears, they're smooth as well. They're nice and straight because it's just a line. Now, we have seen this concept before too, when you're dealing with something that's an x squared. We'd have a parabola, so that would possibly look like that. That's your x squared function. Anything that's an x to the third is going to kind of have this little bump in it. And then x to the fourth looks like a parabola again. X to the fifth looks like a little bump type of graph again. And then anything with an even degree is going to repeat this parabolic shape to it. And anything with an odd degree is going to repeat this bump type of shape to it. Okay, so that's what the note says down here. Now, as we get more and more larger degrees of a polynomial, that area around the origin is going to become flattened out and the graph's going to be steeper at the ends. So if you had a degree of x to the eighth, that graph would look like a parabola, but it would be really flat in the middle and then be really steep on the ends. Okay, so we're going to graph a few polynomial functions here. These are all three of the ones that we're going to graph, but I have individual slides for each of them. Okay, so this first polynomial that we're going to graph is negative x to the third. Now, x to the third, we saw that on the previous slide. It's one of those graphs that kind of has a little bump to it. It starts on the left, and then it goes up, and as you go to the right, you hit the little bump, and then you keep going up further as you go to the right. Okay, but this function is a negative x to the third. So that negative, remember, is going to rotate this graph around the x-axis. So it's going to kind of flip-flop it. It's going to make it upside down. So it should start up high on the left, come down towards the origin, have that little bump, and then go down further to negative infinity on the right. So being able to use those properties of transformations to kind of think about what the graph looks like before you actually start graphing it, that can be really helpful. Now, for this one, you just want to go to your graphing calculator and you want to type in negative x to the third and the y equals, and then go to your table of values. And we're probably going to go from negative 3 to positive 3 when we graph. And we're going to get some extreme values here. Negative 3, negative 27. Obviously, that's not going to fit on our graph, but it's good to have in our table of values. Oops, sorry, that's a negative 1, then a negative 8, and then a negative 27. It's good to have those extremes in our table of values so we can at least have the direction that the graph is going. And notice that for this one, there is a little bit of a pattern that kind of repeats. So it's kind of like a parabola, except the signs change. Oops, I don't know why I have negative 27 there. That's supposed to be positive. So they're all going to be positive up here, and then after the origin, they all become negative. Okay? So I won't be able to graph the negative 3, negative 27, or I'm sorry, negative 3, positive 27, or the positive 3, negative 27. I won't be able to graph those. But I can do negative 2, 2, 3, 4, 5, 8, and negative 1, 1, and then 0, 0, and 1, negative 1, 2, 3, 4, 5, 6, 7, 8. Alright, so there's what our polynomial function will look like. It is one of those ones that has that little bump in the middle. And just like we said, that negative 1 out in front flips it around the x-axis. And again, before we finish graphing, we want to talk about a couple of key features here. We could talk about our domain, which would be all real numbers. We're not limited as to what type of x values we can put into this function, and this graph is going to go forever in both directions. Our range would also be all real numbers. We're not going to be limited in any types of numbers that we get out. We're using all of the y values and all of the x, or all of the positive y and all of the negative y values when we graph. And we want to talk about our x-intercept and our y-intercept. Now we do have an x-intercept for this graph. It's going to be at 0. And our y-intercept is also going to be at 0. Okay, and that's because our graph goes through the origin. It goes through 0, 0. So again, even though this stuff, these four concepts might not be required in your homework, still take time and jot those down and think about those because that's going to make you better at understanding graphs and interpreting their meaning, especially when we get more advanced graphs in the future. Okay, part B. This time we have a polynomial that's a degree of 4. Now, if it was just x to the fourth, that would kind of look like a parabola. It would be really wide in the middle, but it would still be a parabola. It would be opening up because our lead coefficient is positive. But now we have this x minus 2 inside the parentheses here with the x. So if you remember those properties of transformations, that x minus 2 is actually going to move our graph 2 units to the right on our x-axis. So again, keep that in mind as we're making our table of values. And again, you want to go to your graphing calculator, type in that function, use the table of values in your graphing calculator to get some points, and we get some really extreme values right away. We start at 0, 16, and 4, 16. So it only takes 4 or 5 values to get those extreme distances on our graph. And I could probably make this graph a little bit lower, so that way we might be able to fit the 16 on there. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, we have enough room. Okay, so 0, 16, 1, 1, 2, 0, and then 3, 1, and 4, 16. So it's not too wide in the middle, but it's wider than what a traditional parabola might be if it was just x squared. Oop, there we go. And notice that our vertex did shift from the center of 0, 0 over 2 units to the right. So now 2, 0 is going to be our x-intercept. So we definitely want to write that down. So our x-intercept is going to be 2. And our y-intercept, we have that on our graph as well at 16. And remember, if you can't find those values on the graph or in your table of values, okay, right here, there's our y-intercept, and right here, there's our x-intercept. But if you can't see that on your table of values, remember to find the x-intercept, you plug 0 in for y, or in this case, q of x, and then you solve. For your y-intercept, you would plug 0 in for x, and then you would solve that. And then again, we could put down our domain and our range. Our domain is going to be all real numbers, and our range is going to be all real numbers. Oh, no, it's not. Our range is going to be everything greater than 0, greater than or equal to 0. Okay? Okay, now we have negative 2x to the 5th plus 4. So x to the 5th, that's going to be another one of those graphs that has the little bump in it. It's supposed to start on the left and go up and then have a little bump and then keep going up as we move to the right. But our lead coefficient is a negative number, so that means it's going to be rotated around the x-axis. So we're going to start on the positive y values on the left side of the graph. Then we'll come down, we'll go through our little bump, and then we'll go to the negative y values on the right. And that plus 4 means that our intercept is going to be shifted up 4 units. So again, take a moment and think of those characteristics of the graph before you start graphing with your table of values. Again, go to your graphing calculator, type this in, and here we only need to go from negative 2 to positive 2, because at negative 2 we get a really big value of 68. And then we have 6, 4, 2, and negative 60. So again, we have some really big numbers right away, and obviously those aren't going to fit on our graph, but it's good to include them in our table of values so you have a sense of direction. I'm going to shift my graph down just a little bit. Okay, so negative 268 would be way up here. Negative 1, 6, and then 0, 4, 1, 2, and then 2, negative 60 is going to be way down here. So my graph is going to go way up high, kind of have a bump, and then go way down low. Okay, so that bump might not be as spread out as some other graphs. It's probably stretched more because of this negative 2 in the front. Remember that number, that lead coefficient that you multiply by is going to stretch your graph vertically. But it did reflect across the x-axis because it's a negative 2. And we did move up 4 units from the origin. That's because of the plus 4 at the end. So that multiplying by 2 definitely stretches out our graph. It stretches out that flat part in the middle. So my domain would be all real numbers. My range would be all real numbers. I can see my y-intercept at 4. Again, that's in my table of values there. That's on our graph. And then my x-intercept, this one, I know it's there. I just can't tell where exactly. So you could use your graphing calculator to find that. You could trace, or if you go to second calc and try to find your 0, that will tell you where it crosses the x-axis. And our actual value is going to be 1.15. Remember, the other way to find it algebraically is if you're trying to find your x-intercept, plug 0 in for y, or in this case, plug it in for r of x. So you would have 0 equals negative 2 x to the 5th plus 4, and you would solve that. So you would subtract the 4 over, divide by the negative 2, so you'd have 2 equals x to the 5th, and then you'd have to take the 5th root of that. So you want the 5th root of 2, and that should get you 1.15. Okay, so these are the basic concepts of the polynomial graphs that we want to try to practice and understand. These are the nice book graphs, in case the ones I drew weren't nice enough for you. And our last concept that we're going to talk about is the end behavior. Okay? The end behavior of graphs basically depends upon whether or not you have an odd degree or an even degree, and if you have a positive coefficient or a negative coefficient in the front. Okay? So let's take a look at our next slide here. Okay, because this has the nice chart that shows the actual end behaviors. And when we're dealing with end behavior, it focuses more on the behavior of the graph on the right end. So as you're going to positive infinity. So if you have an odd degree, the ends of your graphs are going to be in opposite places. They're going to be going in opposite directions. So think odd, opposite. So one is going to be up and one is down, or one is down and one is up. If your polynomial has an even degree, then they are kind of in agreement, like even agreement. So that means they're going to be going in the same direction. So both ends are going to be going up, or both ends are going to be going down. Now, if you have a positive lead coefficient, then your right end is going to be going up. If you have a negative lead coefficient, then your right end is going to be going down. And that's true for both even and odd degrees. So if you have an even degree that has a positive lead coefficient, both ends go up. Or if you have a negative lead coefficient, then both ends go down. So let's take a look at some examples here. Here in example 2, we just want to determine the end behavior of the polynomial. So we want to look at our degree first of all. So we have negative 2x to the 4th plus 5x to the 3rd plus 4x minus 7. Okay, but the part we really need to focus on is that degree. So we have an even degree. So that's going to tell you that the ends are going to be going in the same direction. So they're both going to be going up or they're both going to be going down. And the way you know if they're going up or down is you look at your lead coefficient. So your lead coefficient is negative, and I'm just going to abbreviate lead coefficient with LC. So that tells you that both ends are going down. And that's basically all we have to do for this example if they want us to just determine the end behavior. You could write it a little more mathematically. You could say that as x goes to negative infinity, y is going to go to negative infinity. And as x goes to positive infinity, y is going to go to negative infinity. So that's the mathematical way to abbreviate what we have written up here. Okay, both ends are going down, so the y values that we get out are going to be negative, and that's true for all the positive values of x and all the negative values of x that we would put into the function. And the book does actually graph that function, so you can see that both ends do go down, and there again, there's that notation. Now your book likes to write it with the y notation first. Personally, I think that's a little confusing just to mentally grasp. So I just like to write it with the x behavior first. It doesn't matter, it's personal preference. Probably more mathematically correct to put the y first, but I think it helps students understand it better because you're used to picking numbers for x and putting them in to the function and getting y values out. So I think it's a little bit easier if you just flip-flop the order. Okay, and along those lines, we're going to talk about the zeros. And the zeros of a function are basically just the solution of a function. And we have already dealt with this in lots of different ways. When you solve a function by factoring and you find x equals whatever, that's your solution to the function because you've set it equal to 0 and you factored it. When you have it in factored form, the stuff in the parentheses will be a factor of the actual function. The values that you get here, x equals c, if c is your solution, that means c is an x-intercept. Okay, so all of these concepts that we've been talking about and all of these characteristics that we pay attention to when we're graphing are all starting to connect now here. And we're going to call those solutions zeros and interpret their meaning so that we can graph functions better and understand them better. So here they give you just a general example. They give you a function p of x equals x squared plus x minus 6. Now if we were to solve that algebraically, we would set it equal to 0 and factor. So they have it factored here. They have x minus 2 and x plus 3. Those are the factors of 6 that would add up to 1. Okay, so that tells you that 2 is a solution. So 2 is a 0. It also tells you that x equals 2 is a solution to the equation. It tells you that x minus 2 is a factor. And it tells you that 2 is an x-intercept. And it would tell you the same information for negative 3 as well. Negative 3 would be a 0. X equals negative 3 is a solution to the equation. X plus 3 is a factor. And then negative 3 would be your other x-intercept. So this graph, when you graphed it, this parabola would go through the x-axis twice. It would cross it at 2 and at negative 3. Okay, so this is the theorem that they have to basically put all of that information together. Okay, it says a polynomial function p of a and p of b have opposite signs then, or if that happens, then there exists at least one value between A and B for which P of C equals 0. So it's just a fancy way of saying that you can find the zeros of the graphs. Okay? And there it's showing an illustration of what a 0 means. Okay, if you put P of A into a function, or P of B into your function, you're going to get those values out. Okay, the zeros would be where it crosses though. Okay, now having the zeros, having the information about the zeros can actually help us graph a little bit better and find more information before we go to our table of values. So you could factor and find the zeros, and you could plot them, and then you could test the points on either side or in between them to figure out where the graph is going to be going, if it's going to be going up or down between those points. We know the characteristics of end behavior as well, so we can make sure that when we draw our graph, it follows those guidelines. And then just basically connect those points so that you know that you have your graph following the proper shape. Okay. So last example here, example 5, they want us to find the zeros. So to do that, we're going to factor. So if you want to set it equal to 0, you can. You don't have to. But we do want to factor the x to the third minus 2x squared minus 3x. So if I'm going to factor that, I'm going to take an x out as a GCF. Remember to always look for that first. Okay, now I have a trinomial that I can factor with guess and check. So the factors of 3 that add up to 2 are going to be 3 and 2. I'm sorry, 3 and 1. And to get them to add to a negative 2, I need the 3 to be negative and the 1 to be positive. Okay, so this is what P of x is still equal to. And then, just like if it was equal to 0 or if it was equal to P of x, we would take each of these little parts and set them equal to 0 and solve. So x is equal to 0, and x minus 3 is equal to 0. So that means x equals 3. And x plus 1 is equal to 0. So that means x is equal to negative 1. Okay, so those are my 3 zeros for this function, my 3 solutions. So that's where the graph is going to cross the x-axis. That's where I'm going to have zeros in my y values, in my table of values. Okay. We could, before we go on to actually graphing it, let's take a moment and just think about some of these other characteristics of the graph. We've got our 3 zeros here. So if you think of it in terms of a number line, we'd have negative 3, I'm sorry, negative 1, 0, and 3. So right there, and right there, and right there, there's 3 points that our graph is going to cross the x-axis. The end behavior of this graph, let's see if it's x to the third. It's going to have a graph that's going to have some kind of little bump in it. The lead coefficient is going to be positive, so you know that if I have a positive lead coefficient, that's going to tell me that the right end is going to be going up. And since it's an odd degree, that tells me that the ends are going to be going in opposite direction, which is a true characteristic of an x to the third type of a graph. It should have those little bumps. So this graph might come up and then have a bump and then go back over. It's going to start down low on the left and come up and through these points, and then it's going to continue to go way up high on the right. Okay. So if I go to the next slide, I can actually graph this. Now, when I'm making my table of values, I can go right to my graphing calculator and find some values. Okay. I want to make sure, though, that I have negative 1 and 0 and 3 on my table of values because those were my x zeros. Those were my x-intercepts, where the graph is going to cross the x-axis. Okay, so I'm going to have 0, 0, and 0 for those values. Okay. So again, I can plot those on my graph. So negative 1, 0, 0, 0, and 3, 0. And then if you wanted to test some points to the left and between and between and to the right of all of those points, we would want to test negative 2. And between negative 1 and 0, I'm going to have to do 1/2. I might have to look at a fraction. I'm sorry, negative 1/2. And then I can also look at what's going to happen for 1 and 2, and then for 4. So those would be the values that you would want to focus on in your table of values in your graphing calculator. So for negative 2, you get a value of 10. 1 will give you negative 4. 2 will give you negative 6. 4 will give you 20. So that's, again, one of those extreme values. And if you want to see the value for negative 1/2, you can go to your table of values and you can change the units that you're graphing or that you're seeing. And at negative 0.5, you actually get 0.875. If you don't know how to change that in your table of values in your calculator, I can show you. Or you could take negative 0.5 and substitute it back into your original function, and you'll get this value out for p of x. Okay, so now we can graph. We'll have negative 2, negative 10. Negative 1, 0, I have negative 1/2, 0.8, so almost up to 1. 0, 0, 1, negative 4. And then 2, negative 6. And then 420. So that's going to be way up here, which is good because I want to start on the left with negative values. Then I have my little bump in the middle here. And then I'm going to go all the way up to my positive values on the right. Okay, so this little bump is more pronounced, but that's because we have other values in our polynomial equation here. We've got an x to the third, and then we have a minus 2x squared, and we have a minus 3x. So multiplying by those and adding and subtracting those values is what's affecting how dramatic that little bump is in the middle. Okay. And what we wrote down about our end behavior is true. The left end's going down, the right end's going up. The ends are in opposite directions. Let's see, we had our x-intercepts here in our table of values. Those are our zeros, or our solutions. And my y-intercept, I could also write down that information. That would be 0. I have 0, 0 right there. It's where it's crossing the y-axis. And remember, if you can't determine that off the graph, plug in 0 for x. Okay. My domain would be all real numbers, and my range would be all real numbers as well. Okay, so lots of little details in today's notes. There's a nicer, prettier graph. There's the book graph for it. Okay, and the homework's not real long, but these graphs do take a little bit more time to do because there's a lot more information that you're asking for before you actually start graphing. So practice these concepts. Remember, I have the solutions worked out in the binder in the classroom. And if you have any questions, come on in and see me before school.